All right, everyone. Thank you for coming. Can everybody hear me okay? Is the audio good? All right, great. Well, my name is Ivan Ramirez, and I'm an engineer with Google. And I've had the pleasure to work with Planet Labs for the last year. And what an amazing ride it has been. Now, as we kick off this event, I wanted to start by telling you a little story about myself. When I first graduated college, I had the privilege of working for NASA at Johnson Space Center in Texas, where I was a console operator for the International Space Station. And one of the most captivating images I have from that experience is seeing the cupola. The cupola is a capsule within the International Space Station with the biggest window on the station, and it allows for spectacular views of the Earth. If you've ever seen an iconic picture of the Earth from space, it was probably taken from this window. Now, when you look at the Earth from space, it's hard to wrap your head around it, but you're looking at 7.5 billion people. You're looking at the Burj Khalifa. You're looking at the most densely populated cities in the world. And you're literally looking at everything humanity has ever accomplished. Imagine all the data that we're looking at. What a thing to gaze out this window. Now, 2 years ago, I was given the opportunity to join Google Cloud. And Google, as you know, is a data-driven company. Our motto is to organize the world's information and make it universally accessible and useful. Never was this goal so apparent to me than when I saw what Google was doing with its Street View project. Google had acquired millions of images of streets across the globe and turned to machine learning to derive insights from that data, which is now known as maps. Standing here today and seeing Planet Labs continue to build a data set of the Earth, deriving data from it, and generating value across multiple industries is, in my opinion, the culmination of what it means to be data-driven and forward-thinking. I'm excited about today's event and to hear what more possibilities can come out of this incredible endeavor Planet Labs has set out to do, which brings us to why we're here today. Planet Labs is making huge breakthroughs in the machine learning space, and in collaborations with Google, Planet Labs is using machine learning technologies to derive insights from their data in a way that we could have only dreamt of a few years ago. Now, we have a group of amazing people here tonight ready to talk about machine learning and the potential possibilities that are possible with this global data set. I hope you enjoy the event, and without further ado, here's Marshall Burek, Assistant Professor in the Department of Earth and Space and Science and Deputy Director at the Center of Food and Security and the Environment at the University of Stanford, who will be our moderator.
Great. Thanks. I'm short, so I'll sit. I think I'm even taller sitting up. Thanks everybody for coming tonight and braving the weather, which I think is turning rainy here, even on a school night. So thanks for coming. It's great to be here. Great to be at this event, and again, thanks to Google for hosting and for Planet for putting it together. I personally am excited to be here because I think we are at an amazing time in our ability to understand the world, and for reasons that Ivan just mentioned. The confluence is, number one, our sort of unprecedented ability to image the world at higher temporal and spatial frequency, thanks to Planet as well as other folks, and then our ability to make sense of that information using the computational tools from folks like Google. And so I'm excited to be here and particularly excited to learn from the other panelists that we've assembled who sort of run the gamut on each part of that, from acquiring the imagery to making sense of it to actually using it in different settings around the world that you'll hear about. So let me give you 2 minutes of background or 1 minute of background on myself, and then I'll let the panelists introduce themselves, and then we'll get to some questions. So I am jointly appointed at Stanford between the Policy School and the Earth Science School, and a co-founder of a startup called Atlas AI that uses satellite imagery to try to measure and understand economic development in poor parts of the world, where we otherwise have really poor data on many outcomes that we want to understand. And understanding these outcomes, we hope, will help decision makers on the ground, and this is everyone from small NGOs to large international organizations, make better decisions about how we shape these outcomes, how we reduce poverty, how we improve economic well-being around the world. So that's a big focus of our research and a focus of the startup that we founded. So we depend heavily on a lot of folks in this room. We work with Planet. We depend heavily on imagery, and we depend heavily on many of the tools that Google has built to help us make sense of this imagery, the computational tools. So again, delighted to be here, and thanks again to these two great organizations who have really changed the game in terms of how we do this work. So I'll stop talking about myself and let the panelists introduce themselves. So we'll just go down the line here, and then I'll start some questions. So Faye, you want to start?
Great. Hi, everybody. Can you hear me? Hello? Does it work? Yeah. Great. So my name is Faye, and I work at Google Cloud. I'm a machine learning specialist for Google Cloud, meaning I work with some of our most interesting customers to tackle their machine learning challenges, as well as infrastructure. On top of that, I'm also very intimately involved with some of our open source projects, such as Qflow, where we're helping people to solve end-to-end machine learning through containerization. Excited to be here.
Hi, everybody. I'm Pierre, and I work at Ever AI. So we're a computer vision company, and we are trying to solve face recognition, face detection, face recognition, and liveness. We're using Google Cloud to analyze like 13 billion pictures that we collected from our users, and we need a lot of scale for that. So that's why, I guess tonight I'm going to be talking about how our pipeline is organized and how we use all the Google technology to compute our, gain insights on our images.
Gopal?
Hello everyone. I'm Gopal. I'm here from Planet. Delighted to be here. So for those of you who don't know, Planet was founded in 2011 by former NASA scientists with the forward-looking vision of being able to image the entirety of the Earth's landmass every day and make daily change visible, accessible, and actionable. So we achieved Mission 1 last year, which is imaging the entirety of the landmass. And we've been focused on making that data more actionable. So I lead the analytics engineering team at Planet, and I'm looking forward to this discussion.
Hi, my name is Vineet Varma. I'm with a company called ExxonMobil, and I'm a long-timer at ExxonMobil. I've spent 28 years in the company, and I've followed this molecule from the well to the wheel. One thing I want to share is this is very interesting to a company like mine because 1 billion people on this planet don't have electricity today, and 2.5 billion people cook with biomass. So to raise the standard of living for people like this at scale, you need technologies like an eye in the sky. So I look forward to the session.
Hello, everyone. My name is Anand Pradhan, and I'm from DCP Midstream. I'm the head of DCP Technology Ventures and Enterprise Services. So DCP Midstream is a energy midstream company. So in an energy value chain, there's upstream companies, midstream companies, and downstream companies. So we are a midstream company. We are one of the largest midstream company in the country. We have about 62,000 miles of pipelines in the country and hundreds of assets in the field, including compressors, processing plants, fractionators, and everything. So we are looking at a number of technologies to solve some of our internal problems, including inspecting the pipelines, leaks in the hydrocarbons, and a lot of other use cases. So we are super excited about, looking into new technologies and super excited to be here joining the team. Thank you.
Great. Thanks, everyone. So as moderator, I'm going to start by asking the questions that I've thought of, and then we're going to turn it over to you guys to ask the questions you've thought of. But first, I get to ask my questions because I have the mic. So I had sort of had three main classes of questions. So here again, we're thinking about this confluence of new and exciting sources of imagery that have changed sort of dramatically, number one. Number two, new computational tools to make sense of this imagery. And then number three, all the use cases that we could imagine for this confluence, right? And so I want to hear about all three of those from our panelists. And so I'm going to start with the imagery on the sort of at the front end here. And so Gopal, I think, is maybe the best to first answer my question, although any of the other panelists should jump in. So tell us about what the imagery landscape looks like now. Maybe, and I think it would be useful for folks who aren't intimately familiar with the rapid evolution of imagery, sort of how it's looked over the last 2 years, what changes have happened, and sort of where you see it going over the next 12 months or 18 months.
Yeah, I think that's a spectacular starter question. So I would say the biggest disruptor to the satellite data landscape has been the emergence of small sats. So tiny satellites size of the loaf of bread. In the case of Earth observation, that's basically a telescope in a box with a radio. Not to trivialize the complexity of like getting that all together, but compared to the legacy satellite systems, which were like big, bulky, they used a different kind of electronic manufacturing system. And the last 5 years has seen new constellations that have been built up through cost-efficient manufacturing processes that enable like many more satellites in space. So if you look at the entire landscape of like satellites, there are over 1,700 of them in orbit today, but the majority of them are centered around communications and different forms of remote sensing. So Earth observation is around 15 or 20% of that collective, and they range over a different, they're over a range of different spatial, spectral, and temporal capabilities. So what we have seen over the last few years has also been the emergence of like going from purely multispectral and infrequent revisit and limited spatial coverage to like multispectral and just purely visible spectrum sampling and more daily revisit and like larger coverage. So that intersection has brought together two changes. One is like you have like more data at like varying resolutions, and more importantly, it's made the entire data landscape very rich. So you do see a collection of different data sources that are all coming together, and that's at the creation end. So it's raised a lot of interesting possibilities, both in terms of opportunities and challenges towards distributing that kind of satellite imagery to customers and consumers of them, and also doing intelligent analysis on them. So that's where I've seen it grow.
So if you could speculate, so that's a great description of sort of how quickly things have changed recently and sort of where we are now. If you could speculate in either on behalf of Planet or just on behalf of yourself, what the evolution in the next 12 months is going to look like, or over the next few years on the imagery collection side itself. So, you know, Planet again has revolutionized our ability to image the world at high temporal frequency, at good spatial frequency. So what do you see in the future? Is it more spectra? Is it even higher resolution? Is it what does the landscape look like in a few years?
I believe it's going to be a mix of these. Like from our perspective, there are a range of different applications that are served with visual imagery, and then there are a range of more traditional as well as new applications in the remote sensing realm that that can be served through hyperspectral and multispectral imagery. So we would see more of those applications come to life because you're having capture at like higher revisit and over larger regions with like more sampling of the spectra. So we would think that as the data grows, the number of or the pool of geospatial and satellite imagery grows, you're going to see new applications which bring them together in interesting ways.
Great. No, thanks. That was a great summary. So speaking of applications, and you mentioned applications, I thought my next question was to think about some of the use cases. And of course, there are a lot of use cases. I assume many folks in the audience are working on use cases here of using this new sort of fire hose of imagery to do various things. But we have a couple of panelists who can speak to that, and so would love to hear their perspectives. So Anand and Vinit, would love to hear your perspectives on how you see this being used either within your organization or with other organizations you work with.
Well, we have a number of use cases, but we are primarily focused on few right now as we start in the this digital transformation of this value chain here. So one of the first one is the right-of-way encroachment. So like I said, we have about 61,000 miles of pipeline in the country in about 14 states. So how we do inspection today? So we inspect through helicopters, we inspect through fixed-wing aircrafts, sometimes we drive across the pipeline because we have to inspect the pipelines, right? So we are looking at how to inspect the pipelines for the encroachment through the satellites. And that means people are building some things near, some structures near the pipeline, or someone is doing some illegal activities around the pipeline. So we are trying to inspect the pipeline. That's one big deal. The second one is around the hydrocarbon leakage. So there could be some hydrocarbon leakage because of various reasons. And sooner we get to it, safer it is for everyone. And in the process, we also make more money because we are not losing our inventory. So we are trying to get to the leakages as soon as possible and fix them as soon as possible. That's the second one. The third one is, I think it's around the environmental events or climate events. So when there are flooding or fire or situations like that, sometimes it is challenging to get near the pipelines and inspect and see what's happening and because people are not around the area and all of that. So we are trying to get to the images through the satellites and kind of take, corrective actions through that. So those are there are a number of others, but these are some of the use cases we are working towards.
Yeah.
You want to add?
So the beauty of going second is all the easy ones have been discussed. So I should have done it the other way around. But anyway, so I'll give you a couple of examples to make this thing real. In the country of Papua New Guinea, we have a pipeline which goes from the Heights plant all the way down to Port Moresby, and half of it is under the sea, so you can't get to it. But to monitor that pipeline, you're going through some territory which there are natives who might be looking at opportunities. So we've got to make sure that that asset is protected. And an example is once you have an earthquake, you have to look at this asset on all aspects to make sure the integrity is maintained. It is a tremendous exercise to do that at scale. And so that's one example of an opportunity area. Now we do have a challenge. If you know where Papua New Guinea is, very high cloud cover. So it's a challenge, which means the Planet guys have to have really high revisit rates. And in fact, we did work on a little project, and we got some tasking over that region, and it was interesting on the temporal revisits on how powerful that can get. So that's just an example of how real and important this thing is. But I'll go down the environmental path, and I think that's very important, especially for my company. Greenhouse gas mitigation. So it might get into the invisible spectrum a little bit, but the use case still is from the sky. And one of the things we are seeing is for carbon capture and sequestration, the grazing patterns of cattle make a big difference, which means if you take a herd of cattle and you put them in a pen and they just graze over that pen, the carbon content in the soil degrades very, very quickly. But if you rotate this cattle herd in different pens and you move it around, there is a significant change in carbon retention on the ground. That has huge implications. And for us, it's techniques like this where we can look at grazing patterns at scale to make a difference is an exciting area. So that's just two examples of areas where we think it is extremely important. Climate change is the other one. What can we do both on the optical side as well as on the non-optical side, the invisible spectrum? So very exciting times.
Thanks, that's great. Follow-up question, do both of you do this sort of work in-house? Do you partner with organizations? How does the work get done?
All the above. So we've got atmospheric scientists in-house. We've got imaging capabilities in-house. In oil and gas, and this is one of the challenges, is we operate in 200 countries. So to do things at scale, you got to get a bird's eye view of things. So we've been using imagery for a long time for environmental mapping, for looking at sites, if there are challenges in terms of locating well sites and so on. So we are very familiar with imaging technologies, both above the surface and especially below the surface for seismic imaging. So we've had that capability. What has changed now is the payloads on the satellites are getting very interesting on the types of sensors. And that goes beyond optical, and that makes things very interesting. And then the algorithms can detect the change in a way where you don't have to have a human in the loop. So that's the change, and we are doing both sides of that.
Yeah, I think it's almost the same situation. We have a hybrid model where we have a lot of competencies in-house around imaging and analytics. But as new technologies come up, we partner with other folks. So there are a lot of interesting folks around the satellite industries, around drones, around new sensor technologies. We also use sensors on some of the fixed-wing aircrafts, and bringing all of that data together and kind of driving some actionable insights out of that. I think we consider that to be our core competency, very strategic competency. That happens in any company. And so it's a continuous evolution, but it's a hybrid model. And we work, if it's a commodity kind of stuff, we partner with our folks, but otherwise we build a lot of things internally.
Great, thanks. That's very insightful. So now I want to turn more to the compute side and hear about sort of how the work gets done computationally, right? What are the new tools? What are the exciting new ways that we're sort of making this happen? And so we have two folks who know a lot about that. So I get, my question is pretty generic. I mean, what's new on the computational side that's relevant to making sense of using this, again, large fire hose of data that we're getting now from Planet and other providers? So, Bay or Pierre?
I prefer, because apparently there's some answers to join first.
Oh, there you go.
So the way Google AI views machine learning is that there are three factors that's very important. First is data. I would imagine people who come from imagery that have problems getting data. The second one is models. This is a little, is it good now? What about now?
Great.
Yep. The second one is models. This is where it gets a little tricky because to build a decent model, you need very good talent. And those talents are very scarce and they're not located all over the place and they're very expensive. It takes a long time to hire. So this is an area where basically Google AI is trying to democratize. I will talk a little bit more about what we're doing there later. The last one is compute. Because the emerging of deep learning, we've discovered that with bigger models, which requires bigger compute, you're able to get better results. But that also means that it's going to require more compute for you to process all your data. So compute is very important. And what cloud brings to the table is that the compute is more scalable, it's more on demand. There's more scalable, specialized compute like GPUs and other specialized ASICs. So coming back to the second point, where I would imagine it's a problem for a lot of you where it's hard to find machine learning engineers to basically build your model. What are you going to do? So some of the things that Google has been working on that we released earlier this year is called AlphaML. So just as the name suggests, what it does is that if you have a domain-specific problem, that's not just recognizing tasks or docs that Google already solved. This would be something like. Is it still not working?
Mic switch number 3.
Okay.
Is it good?
Oh, is it? Okay. Takes some learning on my side too.
Yes.
Yes. So what we released earlier this year with AlphaML is that it helps you solve domain-specific problems. Where basically, if you have custom data, for example, imagery or medical images, where you want to do things like classification and segmentation, where this is not a generalized problem, but a domain-specific problem just for you, what you need to do traditionally is that you need to hire these machine learning scientists. They have to know the domain, and they have to know model building. And they come into your place, and they build the model for you. This is going to take a long time. And a lot of people say that, although there's a lot of papers published around it, but a lot of time it could feel like alchemy. Because some of the things is still not explainable at the moment. So it's a very time-consuming and expensive kind of process. So what AlphaML does give you is that it uses technologies such as transfer learning and neural architecture search to help you find the model without having any machine learning knowledge. So this is perfect for people who have access to both data and compute, because basically this takes care of the model problem for you automatically. So given your data and given compute that you're able to provide it, AlphaML is going to generate the model that we think is best for your data. So I talk about some of the technology that it utilizes, such as transfer learning. So basically, the general idea of transfer learning, for those of you who are not familiar, is that you start with something more generalized, and then you train that generalized model on your specific data so that it will be more customized to you. And another one is neural architecture search, where it kind of ties into where compute is important, because a lot of times it's hard to reason what kind of architecture is going to work or not. So basically the idea is that you would keep tuning these type of parameters by throwing a lot of GPUs or a lot of specialized hardware at it to make it faster, to parallelize it, so that you'll be able to get the best result. Here to you.
Thank you.
So we obviously have the same kind of a trouble here, but we decided to go with hiring the talent and not hiring AutoML to do our models. So I'm going to talk about a different kind of a problem we have. So in my company, we acquire data through a photo album app. Think about like Google Photo, but just another name. And so we have users uploading a lot of pictures to our servers, and we need to analyze all these pictures. So the problem we quickly had is like we ended up with 13 billion images, and it's obviously very hard to run in a timely fashion to analyze all the data. So we were looking. Our first problem was to, instead of spending like weeks and weeks running like a few machines just analyzing those data, we needed to parallelize that a lot. And on Google Cloud, you have like this platform Dataflow, a product called Dataflow, which let us like parallelize this processing very well. So we basically run our model on that. We use Dataflow to run our model on those images, where we download the image, we process, find the faces, we compute the embeddings, and then we need to store that back and give that, make that available to our data scientists. And so the second big problem that we had was that the data scientists like change their minds very often, and so instead of storing the embedding into like a Google Cloud storage and a Google Cloud bucket, like and just having like grouping those embeddings by in big files of thousands and thousands of embeddings. Well, they want to be able to mix and match their embeddings. So they want to be able to select all the embeddings computed from faces where the image was taken in that part of the world, where we identified a male or female, maybe with some specific type of occlusions, or maybe front-facing faces, or people looking up or down, or things like that. And one of the challenges we had is like being able to let them like select whatever they wanted. So after trying a lot of different methods with simple CSVs, where they could just like select and then we don't know the proper image, we just put everything into BigQuery. So it's not really meant to ingest like image data, but we put everything into BigQuery, and right now they can select like simple SQL. They can just select whatever they want for their data set, and then construct different type of data set depending on the problems that they are working on right now. And that's mainly the two big problems that we had, and we need more and more compute for those two problems. So more and more scale, and we do not, now we need to use GPUs to even like go faster to help our processing and to make the process faster.
See if I can use this mic without it freaking out. I'm gonna try. Okay, thanks. Might back up a little bit where I was before. Better? All right. Thanks. Follow-up question. Maybe this is more for Faye, but thinking specifically about the marriage of satellite imagery and compute, do you see either on these sort of automated ML platforms or on just, I guess, broader computational tools, do you see the development either now or in the future of specific tools that could really help us make breakthroughs with this new sort of satellite-specific information that we're getting?
I would say that because is it on? Is it on now? Is it? Yeah. I see something. Hello?
Yes.
Does it work? Great. Yeah, I would say that satellite imaging is something that we've seen a lot of interesting progress in. For example, we worked with the European defense arm of Airbus to basically distinguish whether or not a pixel on the satellite imagery is null or is it cloud. That's very important to the imagery because that's going to be very different things to what we're looking for. I would say that specifically to satellite imaging, I think there's a lot of progress to be made on combining the location of the data as well as the content of the image, because as natural to geospatial data, the location matters as well as the content. So that's something that we're keenly interested in and excited to work with our customers on. I would say that in terms of transfer learning or AutoML, you will have to start with a model that's suitable for the general problem. Because some of our models are probably trained from our large set of Google images, they might not be the best fit for imagery data, and that's something that for you to consider as well.
Okay, great, thanks. So my last set of questions, and then really excited to get the conversation going with you guys in the audience. So it's more around constraints. So there are a lot of different parts of the puzzle that have to work for this to be successful, right? So we talked about the input, so let's think, not just satellite imagery, but let's think about imagery as the main input. Outputs are labels, right? The thing we're trying to predict. The model that sits in between those. So there's the development of the model, and then there's the people or the machine to run the model, right? So you can think about that as a talent problem, either a computational talent problem or an actual person needing to do it. And so that's a computational question. And then you have the adoption problem, right? So maybe you can make a good prediction, but you have to convince people that it should replace the current tool that they're using now, presuming they're using a tool. And so you could see constraints sort of all along that pipeline. And so I'd be interested to hear from all of you, and Pierre, you spoke to a few of these, where you see the constraints and how you see us making progress on this constraint. What can we do to sort of break through? So let's just go down the,
I'm going to go
Peter,
first.
please.
So on the technical side, I can speak to it, but I think the limiting factor here is not the technical capability. I think the compute, the machine learning models, the acquisition of imagery, fantastic, we'll get there. But we have an issue, and here's the reason why we have an issue in terms of adoption, and I think we can crack it. Humans naturally can walk and they can swim, but humans naturally cannot fly. Just think about what I said. So we have to fake it, and you have to think like a bird. And I'll give you an example because I've been in this space on use cases for 5 years now. And as a kid, I used to have homing pigeons. And homing pigeons, you get to learn birds. So if there is one secret I will tell you is, if you want to get good use cases from the sky, you have to understand birds. And I'll give you a couple of examples. An eagle, it flies and it does two things. It explores and then exploits. So first it'll explore and see which areas it can get prey. And then it'll go ahead and zero in on that area and pick up that mouse or that rat from the field. So this concept of explore and exploit I don't know if it was done purposely, but we have these satellites, which are the DoveSats at Planet, which are low res. It's more explore. The exploit comes on the higher res. So you can look at it as queue and task, but that's what an eagle does. Think about the owl. It does it at night. It does it in a different way. So now when you think about use cases in businesses, we have a cognitive block because people don't think like birds. And this changes business models, but you have to kind of reinvent the way we are thinking about the problem. And that's not easy. It is hard, as most of the companies can tell, because you have to really step back and say, this overview effect from the sky, what does it give me? And how can I think of things differently? You can't solve the same problems the same way. You got to think of it slightly differently. And to me, that is a big challenge, because if you look at my business, we are in functional silos in the company: explore, produce, refine, and sell. When you get up in the sky, you can see the whole company at once. The sky integrates my business. We can see stuff from the sky which sits on intersections, on adjacencies, on white spaces, which we never saw before. And so the softer aspect of why the use cases are a little difficult, I thought I'll at least challenge you a little bit with thinking about what I said. And once you get into this mindset of a bird, things start coming to you a lot easier. The tier 1 things are very easy. You can pick up the right of way on the pipeline. The tier 2 and 3 is where it gets interesting. So I'll just pause there on the softer things.
I go next? Okay. He's happily giving it to me. So, yeah. So I think there are a few constraints. So I'll highlight some of them. So one of the thing is, the way I think about it is, there's, like you said, there's an input, there's an output, and there's an outcome. Okay? So enterprises always look for outcome. And sooner it comes, better it is. Right? So I'm sure Planet is not established to just sell pixels or photographs, right? You have to generate some value for the enterprises that you are supporting. And how soon can you get to that outcome is critical. So today we use satellites for some things. We use fixed wing aircrafts for some things. How do you bring all of that data together and give actionable insights? But that's not sufficient, right? Actionable insights is okay for the lab or for a few engineers maybe, right? But then you have to get to a point where those actionable insights are transferred into defined actions, right? Reasonable actions, and the actions are taken in the field or somewhere, and the outcome is proven. So there's I think, long tail, or like in the retail, what do we call it? It is the last mile, right? Taking all of these technologies and brilliant things and solving the last mile and fixing that problem, it's still a challenge with a lot of companies. And typically when you come to, I think, a lot of enterprises, not retail world, but enterprise world, the companies are not very technically savvy. They are not there in terms of, in terms of digital transformation, they are not leading from forefront. Folks are out there for like 30 years, 40 years. That's typical kind of life of how long they have been there in the company. So getting into those actionable insights is not sufficient. We have to drive all the way to the actions and the outcome. That's what drives the engagement from the organization. I think that's one big deal. The second thing we look at it is, at DCP, we are trying to drive digital transformation at the enterprise level. So you cannot bring a satellite and few technologies and trying to transform just that vertical. There's a lot of connecting dots in the enterprise of how the value is created. It is not just a satellite. It comes to GIS engineers. It comes to field. There's a finance guy who is involved. There's HR folks who are involved. There are operations folks who are involved. There are transformation folks who are involved. So we try to drive it at the enterprise level, and I think that's one of the things that that drives a constraint in the organization. I think those are some of the things that I want to highlight. Yeah.
Okay, thanks. So less on the technical side than I was expecting, more on the sort of operational side or even vision side. So that's interesting. How about other folks? Gopal?
Well,
Pierre?
on the
Pierre has the mic.
on the technical side, for more on the technical side, one of our big problems is we have we lack the right data. So we have a lot of images and 13 billion of them. But that's too much for any human to kind of look and see what's in there. So we do have some ground truths on them. But the ground truth is maybe sometimes inaccurate, or we just don't have enough ground truths on all the images. And so I guess what we need to improve our models is the compute side of things is fine. Like we have what we need, but we need like better data. We need more better ground truths, and also when a data scientist is trying to make a model, the model will be biased a little bit depending on what you feed into during training, or what you feed the model during training. And so we're always trying to find the right data to feed to the model so that we have the best outcome and the best accuracy in the end. So one of our challenges is to learn how to explore our data set and learn enough insights about our data set to be able to train a model that is with the least gaps possible and bias possible and have the best model, the best accuracy in the end. And you need to be creative, and you need to invent sometimes very convoluted ways to kind of scan through the data set. And so we have some, I believe, smart people in our team, and so we kind of sometimes we come up with strange things, but it kind of works. Sometimes we're not sure what. And that's also one of our big problems. Like sometimes we end up with an outcome, and we're not sure how we got there. Like the model just output something, and we're like, okay, I was expecting something different, but I guess it works. So we're also working on that, like model explainability, like trying to explain what the model used in the image to determine come to the outcome. That's our next, I would say, problems and what we're gonna try to solve.
Great, thanks. Gopal or Faye? Gopal? Right.
Yeah, so my mind's still on the think like a bird perspective when you shared with us. So we're just trying to wake up from it. That's why.
Are you an owl or an eagle?
I have no option. No. So great perspective. I do believe that the central, one of the defining characteristics of like satellite imagery compared to other computer vision tasks when you try to do computer vision on satellite imagery is developing this purely on nadir kind of perspective, and thinking through how can you identify, detect, localize, and classify things from from a singular perspective rather than how we normally recognize and identify things. So I believe that's relevant, very relevant. I also feel from the perspective of like customers who've been using Planet data and using satellite imagery for a while, who are lacking some of the analytic capability, and they are seeking an analytic solution very quickly. Seeking an analytic solution, you see them go down the path of like 3 dimensions. The first one being they want the solution really quick once they explain the problem to you. Secondly, they want it to be performant in the sense it works all the time. And thirdly, they want it to scale. It works in all regions. And those 3 elements are kind of what I call the trilemma. You have you want scale, you want quick speed, and you want performance. It's just the hardest thing to do. So the way you normally start is compromising on one of the dimensions and then improving on the getting to a good point on 2 of them and then scaling down the third. So I would also say from the challenges in data around geospatial, which is the step beyond what we think of just Earth observation imagery, is one, you have like tremendous growth in the volume of data you have to deal with, and that just forces you down the path of going on the cloud. So cloud native processing, I think, is central to our workflows in the future. Secondly, I think it's the element of making data analysis ready. So when you seek data from multiple sources, then you want to be able to bring them together in a form where quick analysis is possible. And the third most important thing, I believe, is like getting to multimodality. So being able to use different kinds of data sets together. So derived feeds from Earth observations is part of the story. Often you got to conflate that or bring that together with like social data and location-aware data. And that requires a different set of expertise. And that resides in very bespoke data science teams today in different organizations. So as technology, as these capabilities mature, you're going to see more of these providers provide more value-added insights. So that's going to be some tremendous area for growth for all of us.
I was going to add something. So Pierre mentioned explainability of AI. That's a big deal. When a model comes up with something and taps a human on the shoulder, why was that the case? Why the tap? If you can't explain it, the human won't buy it. And so explainability of AI is very interesting. But I think we are in a very unique position with computer vision, because when you make a recommendation, it might be mashed up with other data, which is not satellite imagery data. But you have a vision example, you can show the human on what triggered that cue. That is very, very powerful for explainability. So Rich Karuna does some work at Microsoft Research in this space, but this is a breakthrough when we do analytics and you can show the reason why the model came up with something. Very, very powerful. And I'd like to see more of that. The second one is this concept of an archive. So this eagle in the sky called Planet, they have an archive 4 or 5 years old. And that intrigues me more than anything else. There's a source of truth which is being built. So now you can look at this temporal change and you got to think about that. And that's something very, very powerful, is going through the archive which is being built. And do we have complementary data sets to prosecute that archive? And then finally, from a technical perspective, being able to infer at an edge device, even up to the satellite imagery finally, because compute will get so good, so that you can control at the edge. Think about autonomous vehicles and things like that. Think about drones and things like that. So this evolution, as it goes further, I like to see this ability get to the edge. Crazy good.
All right, great, thanks. Faye, maybe Google's unconstrained, or do you have something?
We have no problem at all.
Okay, that's what I thought.
Microphone. Is it working? Yeah. Okay. Yeah. So I think the general area of, is it on?
Right by your face, maybe?
Is it on?
No. All right, use this one.
Hello.
That one's good. Use that one. We'll retire this one.
Hi. Great. I think the field of machine learning. Hello. This field is changing very quickly, and we're seeing a lot of challenges coming from this field. I'm just going to talk about 3 of them that I see most common. So the first one I see a lot is developer operations. A lot of people, like engineers, they know the DevOps is kind of a more or less solved problem in general engineering, but in machine learning engineering, it's not solved at all. The machine learning engineers or data scientists, they use so many different tools, and their tools are so fragmented. And if you go to a different company, they have different things across the stack, like almost from bottom to top. So in this very bespoke solution, how do you make sure that your team is acting very effectively? Because you're basically gluing tools, input and outputs from different tools together. So that's one thing that's moving very quickly in the industry. Basically, one trend is to containerize each step and focus more on end-to-end machine learning. Because a lot of people, when they think about machine learning, they think it's all about training, because training is the most important part of machine learning. But as a matter of fact, it's really part of it. It's a small part of it. A lot of times we hear people say, hey, it took me a couple of weeks to develop this model, but then it took me 6 months to put this model in production. That really just shows how immature the tools are today. So that's really what we see. Basically, we go to any company and they have this problem, even the most advanced, sophisticated companies. And the second problem that I see in machine learning is more on the model side, is on repeatability. Our team was talking to Ian Goodfellow, a very prominent machine learning researcher at Google, and even Ian Goodfellow himself have trouble reproducing his own paper from a couple months ago. I think it kind of ties back into the tools problem when I talked about earlier, because if you have an environment where you upgrade from Python 2 to Python 3, maybe you're not able to reproduce your result. And that's just like one of the many, many factors that could change in the course of weeks. And if you cannot repeat your result, how are you going to make this a science? How are you going to make this an engineering effort, right? So repeatability is something that a lot of organizations care about. And the third challenge I see is a lot of companies are thinking about how to put humans in the loop. The most common way for this to happen is basically the humans would label the data, and then you will train the data in bulk. But the world is changing so fast, and you want your model to be able to react quickly to your real world, right? You want your model to be real time, just as your data come back in real time. So how do you think about putting human in the loop as part of training? And maybe that could be continuous learning. Maybe that could be something that requires less data, something that gets model feedback in real time. Yeah, so those are the three challenges I see. Of course, there are a lot more, many, many more interesting challenges, but these are the three on my mind.
Good to hear that Google is constrained, at least in some way. Okay, you guys have waited patiently, and so we'd love to hear from you. So anyone who has a question or a comment or a question they want to phrase as a comment, raise your hand. I think we won't pass mics around, probably too slow. I think the room's, or do you want to, Scott?
Do we have two left?
We have two working left. Okay, we can pass them around. So please give us your name quickly, maybe where you come from. Interpret it however you want, and succinct question or comment. Sir.
Hi, Glenn Speckert, SpecTech. Geospatial data has got a special characteristic in that it's always about the same place. If you've got 1 million images of my house, it's various different things. So over time, you're going to be putting out not just imagery, but these derived data sets and analyses. In your interfaces, the question is how do you assure the quality? Let's suppose a drone is making a decision of where to land autonomously, and it's looking for a flat spot, and you told me I could go here, and when I went there, something happened. It wasn't safe, or it wasn't as predicted. So what are the liabilities of the data and reliability and that sort of thing, especially in this era of fake news?
Who wants to touch that one? Liability? Yeah, I'm going to try to tell you, but
Yeah.
Thanks.
Yes, I think the first thing I would say is like almost often the data is protected with some kind of disclaimer, which will prevent you from like being able to like deal with liability later. But I think what you're trying to also get to is getting to more recent capture. So the cadence over which you capture imagery and how recent your truth system is, where you're controlling the drone or controlling your unmanned aerial vehicle, is going to drive the confidence with which those kind of situations don't happen. Right. Right. So you need to develop some kind of recency bias if that's of critical importance to your application.
Which gets to this concept of the model for ground truth has to be activated constantly, and that's very, very important. We get into it for fugitive emissions. What's on the ground and what are you seeing from the sky? Are we using the same baseline or not? I'll leave you with another analogy in case the eagle doesn't excite you enough. When humans get good with something, they use it in warfare. So we started armies first, right? Then we figured out, oh, we know how to swim, so the navies to attack. But the Air Force came last. Just think about it. It came last, but it is the most lethal in terms of what we do. But you can't win a war from the air. You got to get boots on the ground. And that's the ground truth element. And even in warfare right now, you look at the armed forces, it's an agile force on the front line. They'll call in air cover because the ground truth is good, and they'll soften the target before they go in. So that's, it's another way to think about it, but this ground truth business is very, very important, especially in the fugitive emission space too.
Hello, Ralph Lafferty, Orbital Insight. Quick question for you around collection. It was announced this week that certain cloud providers are setting up their own infrastructure to be able to do collection from satellites. And curious about what that means to Google and if that's the intent of Google as well, and what that means to the hardware marketplace.
We'll start there. Fair. Specific on that? No? Yeah, it was a good question. Yeah.
I'm
Wrong panelists. Anyone in the audience want to chime in on that one?
I'm not Google or in the hardware marketplace. Otherwise, I would have an analogy.
Yeah. Thanks for that context.
Hey, folks, and for our closing remarks, we have ex-NASA scientist and founder and CEO of Planet Labs, Will Marshall. Thanks for joining us.
Hey, no worries. Well, this is a little bit impromptu, and we have a rocket launch to get back to very soon. In literally a couple of hours, I just got a text with the rocket on the pad in India. And it's a pretty exciting week because we have 2 rockets going up in 1 week because we've got a SpaceX rocket going on Saturday. But anyway, I'm delighted to co-host this event, and I'm glad everyone could come. I think what we're trying to do at Planet in terms of the data set that we're trying to build of daily imaging of the planet, and what Google is offering in terms of the cloud and the machine learning capabilities creates potentially together a bit of an platform for an ecosystem of folks like yourselves building apps and services on the back of that. And we really want to help support that ecosystem. And so I'm really excited that we all get to have this sort of conversation. I'm around for the next sort of 10 or 20 minutes if anyone wants to grab me before we get back to the launch. But about specific collaboration, and there's plenty of Planeteers in the room to chat about collaboration. But with that, I just want to say thanks for coming along. And if you want access to our data, please speak to some of the Planeteers here about how to do that. We're really excited to partner with whoever wants to build applications and services on the top of daily imaging of the planet. Thanks very much, everyone.
Well, if everybody wants to head out to the foyer, grab another drink, talk to all of our esteemed panelists, our great moderator, and also on the back of your cards, if you want to test out some of these methods, we have a free month or quick labs, big data, machine learning. Just go ahead and sign up on that unique code. Thanks for coming out, everyone.
That was a little longer. Thanks. Yeah. Thank you. Great meeting you.